So in our first session for today, we're going to continue with our iOS firewall discussion. We're going to talk about the transparent firewall in iOS and then how to configure it with content-based access control and with the zone-based policy firewall. Now, before we get to that, I want to do a quick review of the routed firewall, both for the CBAC and for the zone-based firewall. We're not going to go through all the configurations again that we've done, but we want to talk about just what is the logic of it and how that is going to change when we start to introduce the transparent firewall. So let's take a look at the previous topology that we were using for the iOS firewall. And previously we had router 3 configured as our firewall, both with the CBAC process and with the zone-based policy firewall. And we could see in this particular case we have a normal routing design where router 3 has 3 different segments. They're in 3 different VLANs. They're in 3 different IP subnets. So it means that when traffic wants to move between these interfaces, first router 3 needs to make a routing decision. So this in turn means we have some sort of routing protocol, whether we're doing static routing or IGPs like OSPF, EHRP, maybe BGP routing. But it's important to note that the security feature set and the firewall filtering is independent from the routing decision. Now, we'll come back to this and talk about this more when we get to our VPN and we get to our network address translation. This is a very key important point to remember, that the routing process is completely independent of firewalling, or it's completely independent of the crypto process. So we always need to make sure that routing is solved first before we can do any type of filtering or we can do any type of IPsec VPNs like our crypto configs. Now here we had a couple different configurations where we had the interfaces from router 1 to 3 and from 3 to the test PC. These were considered the inside interfaces, and then out to router 2, this was considered our outside interface. So of course then the basic logic of the firewall filtering is that we want to watch the traffic as it is coming in on the inside interface going to the outside. And then this entry here, this inspection, is going to create the state information in our session table. So whether this is with CBAC, which we would look at with the show IP inspect sessions, or whether this was with the zone-based policy firewall, where we could say show policy map type inspect zone pair sessions, or we could say show zone policy show zone firewall sessions, I should say. But in either case, we're creating the state information. Then when traffic is returning back from the outside in, we're going to check the state table first to see if the session is allowed. If it's not allowed, then we're going to fall back to the interface access list, which then could have our manual exceptions or fall down to our implicit or even our explicit deny. Now, the transparent firewall is going to work with this same exact logic, that as traffic is moving between the interfaces, we're creating the information in the state table. The main difference between them, though, is that we're not going to be routing the traffic between the interfaces. We are going to be bridging the traffic. Now, we'll see that this is also supported in ASA when we're dealing with single context mode or multi-context mode. Then we could run single context transparent, multi-context transparent, or both variations in the routed firewall, which is the default, and likewise in the case of the regular iOS firewall. So this is supported both with CBAC and with the zone firewall. The zone firewall, see, from a documentation point of view, they don't give many examples of how this works. So we do need to talk about just the general bridging logic first before we get into tying the bridging in with the actual firewall feature set. Now, the main change in the design here, if we look at the difference between the routed firewall and then the transparent firewall, is in this case we're going to be using router 2 as our firewall. We have the inside interface and we have the outside interface. They're still in 2 different VLANs, so they're in separate broadcast domains here, but the difference is that they're going to be in a single IP subnet. So we could think of router 2 here basically as an Ethernet switch that's taking packets in one access port and then bridging them out another access port But in the middle, we have our routed interface, basically like our VLAN interface, that could be used to apply policy to the traffic as it's moving through the switch, or in this case, the router. Now, the way that this is specifically implemented is with kind of a legacy feature that you don't see too often anymore, that is called the integrated routing and bridging, or the IRB feature, and the previous version of that, the concurrent routing and bridging, or the CRB feature. Now, what these two features do, CRB and IRB, is to allow the router to route protocols on certain interfaces and then to bridge protocols on other sets of interfaces, or to intermix the two between them. So the logic is going to be very similar to a catalyst switch that has a VLAN interface, where the VLAN interface is basically the routed interface that represents the bridge domain, or the switching domain. Then from the access ports, or essentially the interfaces that are in the bridge group on the router, that's the traffic is going to be bridged directly between them. If it needs to route to another portion of the network, it can use the bridge virtual interface, which is going to be similar to our VLAN interface on the catalyst switches. So like I mentioned, this is going to be a similar logic to how the ASA does it, that both ASA and iOS do support the transparent firewall. So the interfaces are going to be in the same subnet, but they're going to be in different VLANs. And we're using the router in this case to bridge those particular VLANs together. Now, this would be very similar to other designs if instead of doing a firewall here, if this was an IPS, where we're doing inline IPS and the inside and the outside interface are in separate VLANs, but both in the same IP subnet. And we'll see likewise with some of our other devices as well. So different VLANs, but the same subnet, and then the router is going to be used to bridge the traffic together. So this means that the router is going to need to participate in the layer 2 bridging domain. We're basically turning it into a switch, and now it's going to make its decision based on layer 2 MAC addresses as opposed to our normal layer 3 forwarding. So we don't need to run a routing protocol in this case. If we don't want to talk to the routing domain, if we're doing just basic layer 2 bridging, we're going to have the inside and the outside interfaces in the same bridge domain. Then the router is going to make its decision based on MAC addresses as opposed to the layer 3 information. Now, ultimately, the session table for the firewall is still going to control which traffic is going to be allowed and which traffic is going to be dropped. So from a configuration point of view, we're still going to have our inspection rules that are watching traffic that leave the network. Then when traffic tries to return, we're going to check the session table first. If there's not a match in the session table, then we can fall down to the access list that we have applied in the interface, and then that can do our manual exceptions, like if we need to allow the routing control plane through, or other control plane protocols, maybe non-standard protocols like our trace routes that we previously saw. We can use the inbound ACL in the reverse direction as an exception to essentially poke holes in the firewall. Now, as I mentioned, this is supported both with CBAC and with zone-based policy firewall. Their configuration is going to be essentially the same as normal. So the inspection rules and the zones are going to be applied on the physical interfaces, but the routing is going to be done on the bridge virtual interface, the BVI, we'll see. Now, there's a question here, why would we want to do this in the first place? The main reason why is that if we already have a current routing domain set up and we want to introduce firewalling, anytime that we do a routed firewall like ASA in its default mode, or the routers running CBAC or zone-based policy firewall, it means that's another layer 3 hop that we need to deal with in the overall design. So let's say, for example, that we have a basic setup where we have our ISP and we're peering with them. Let's say that this is a LAN segment and we have some router at the edge. We have router 1 here. Okay, then we have our own internal network. Now at this point, we don't have any type of security set up other than just basic stateless access list, let's say, on the router for traffic that comes in. But now we want to change this design and we want to add some sort of firewall in the path. Now typically when we're doing these peerings to the service provider, we're going to get some sort of address on this link that's like a /30 or a /31. Because basically this is a point-to-point link that is going between the edge router and the service provider. So if we want to introduce a firewall here in the routed mode, it means that we now need to terminate the routing domain on the firewall, and it may not support the particular policy that we want. It may not support the BGP routing, or maybe we're doing, for example, we could be doing other more complicated things like IP-SLA, where we're doing tracking of the link to the ISP. So the firewall's features, normally these are focused on filtering, not necessarily on advanced routing functionality. And if we introduce the firewall as the layer 3 hop, it limits some of the application of what we can do with the actual regular routers. Now, if we were to introduce this as a transparent firewall, basically the only thing that we would need to do is to either move the physical links or add like another switch in between, where we could switch the traffic to the firewall on the outside interface and then switch the traffic back on the inside link. And we would not need to change any of the configuration on our edge router. And likewise, the ISP wouldn't have to change anything in their routing design. So it really depends on the particular application. Do you want the firewall to be involved as a layer 3 device? It might be easier if we're doing just layer 2 when we're not needing anything like IPsec VPN applications. So we'll see that when we get to the ASA, if you turn the transparent firewall on, there's a lot of other features that you lose, mainly them being anything that is IPsec VPN related. So you cannot terminate LAN to LAN, you cannot terminate remote access if you're running in transparent firewall. So it really depends, what is the role of the firewall going to be? Is it just for filtering, or is it going to be for other advanced security applications as well, like the IPsec VPNs? So in our current configuration, basically I have the routers just set up with their interfaces in the VLANs. We have the test PC that we're going to do some basic application testing from behind router 3, but I do not have any of the bridging set up. So the first thing that we need to do is just to get basic connectivity between router 3 and router 1 by bridging the traffic in on the inside interface of router 2, and then sending the traffic out on the outside interface. Now, as I mentioned, the feature that allows us to do this is it's independent of the firewalling config, and it is a configuration that is known as either integrated routing and bridging, which is the IRB feature, or the concurrent routing and bridging, CRB feature, which basically allows the router to route IP on some links and then bridge IP on other ones. Now, you will see from a documentation point of view, there are some minor examples of this under security. So from the main documentation page, if we go to Products, iOS, regular iOS, let's say 15.2t, Configuration Guides, then down to Securing the Data Plane, and then under Content-Based Access Control. Now, as I mentioned, this is also supported under the Zone-Based Policy Firewall, but when we look at the Zone Firewall configuration, under just this generic document, which is Zone-Based Policy Firewall, there is a section that talks about Transparent Firewall, but they really don't give much information about it. There's no examples here of how to configure this. It's essentially just taking your normal zone firewall configuration, combining it with IRB, and then applying the zones on the physical links. Now, in the case of the other document with this, which is the content-based access control, they do have a separate section here that is the transparent iOS firewall at the end. So this one does give a full example of how to configure this, and then we'll also see there are some other minor design considerations we need to take into account, like what happens with DHCP traffic going through the firewall, because the applications are going to be processed a little bit differently when we're doing bridging versus doing regular routing. So if you haven't seen this document, I would recommend to take a look at it and read through just the general information about it. In our particular case here, we're mainly focusing on just how to do the implementation. So under this section here, how to configure the transparent firewall, the first thing we need to do is to configure the bridging. Now, somebody had a question here, what is the difference between integrated routing and bridging and concurrent routing and bridging? The main difference is, do we want to also route for that segment, or do we just want to do bridging? So if we take a look at just from a more general case, this doesn't necessarily relate to firewalling, it just has to do with the routing versus bridging logic on regular iOS. Now, from the original implementation, the router supported routing for a protocol, let's say routing for IP version 4, and then bridging for a different protocol stack, let's say IPX, for example, but not both routing and bridging at the same time. So they first introduced the concurrent routing and bridging feature, which means that on interfaces, let's say E0 and E1, we could route IP, and then on interfaces E2 and E3, we could bridge IP, but we're not mixing the two of them together. So essentially, the routed domain is completely separate from the bridge domain, and they're not able to communicate with each other. So it essentially means that we're just concurrently running routing and bridging at the same time, but it's similar to having two separate devices doing it, where we had one physical router and one physical bridge, because there's no inter-process communication between the two of them. Now, the second variation of this, which is the integrated routing and bridging, is where we can say on interface E0 and interface E1, I want to bridge IP, but then on interface E2, I want to route IP, but at the same time, I want traffic to be able to come in on Ethernet 2 and then route into the bridge domain. So we want to integrate the two of them together. Now, the main difference from an implementation point of view is that this integrated routing and bridging feature has a logical interface which is called the Bridge Virtual Interface, the BVI, that represents the bridge domain to the routed domain. And that's what they're talking about here in the documentation, that if you don't configure the Bridge Virtual Interface, we have to disable IP routing, because with the concurrent routing and bridging feature, you can either route or bridge, but not both at the same time on the same interfaces. So if we configure the BVI, that's doing integrated routing and bridging, where we can combine both of them together. Okay, but really this only matters if we want the firewall itself to be able to participate in that routing domain. So if we look at our particular design here, let's say that router 3 is going to have the address 136.1.123.3. Router 1 is going to have the address 136.1.123.1. These two routers are in the same IP subnet, but they're in two different VLANs. So router 2 is simply going to bridge the traffic together. Now on router 2, if we also had another link, let's say gig 0/1, that was in a different subnet, 136.1.100.0/24. And if we want traffic to come in here and then be able to exit out the bridge domain, this means we need to do integrated routing and bridging, that we would have to have a BVI interface that has an IP address in this subnet, the one that belongs to the bridge domain, and then we could run normal routing protocols. We could run EHRP, for example, or OSPF, moving traffic between the routed domain and the bridge domain. So this is essentially the same exact thing that the Catalyst switches are doing, except they're accelerating it in hardware. Usually the router is going to do this in software when it's bridging the traffic between the interfaces. So in the case of the switches, that VLAN interface, we call it the Switched Virtual Interface, the SVI. In the case of the routers here, at the Bridge Virtual Interface, the BVI. But they're essentially doing the exact same thing, which is to represent the bridge domain to the routed domain. Okay, so if we look back at the documentation, it says first thing we need to do is configure a bridge group. And this is essentially the same thing as configuring a VLAN on a Catalyst switch. So we configure a bridge number. This is essentially the VLAN number. and then we turn spanning tree on. So normally we say like bridge 1 protocol IEEE. That runs normal IEEE spanning tree. Then at the physical links, we put the interfaces into the bridge group. This would be the equivalent in the catalyst switches of saying switch port access VLAN 1, or whatever the particular bridge group name is. Now this here, the bridge IRB and the interface BVI, this is if we also want to route traffic into the bridge domain, but you don't necessarily have to do this if the router is just doing bridging. So let's take a look at that first step then, which is we're just trying to get router 3 and router 1 to communicate with each other. So on router 3, let's look at the show IP interface brief. Right now we have the interface towards the test PC configured, and then we have our interface F00.23. Okay, this is going to be the segment that is essentially bridged through router 2. So from router 3's perspective, there's nothing special about this configuration. We simply have the interface, and in this case we're doing trunking encapsulation on the switch, so we're doing a router on a stick here. But from router 3's point of view, there's nothing special about this. So we simply have the IP subnet configured. And then the same is true on router 1. So on router 1, if we show IP interface brief, we have interface gig00.24, which is in VLAN 24. So again, the key point being here that router 3 and router 1, they're not in the same VLAN, but they are going to be in the same IP subnet. So on router 1, we'll say on this link, gig0024, IP address is 136.1.123.1/24. Now, of course, if we go to send traffic between them, as it stands now, they're not going to be able to reach each other because they're not in the same broadcast domain. So they're not going to hear each other's ARP traffic. They're not going to hear any broadcast or unicast traffic between them. So the next step is we need to configure router 2 to bridge the traffic between these two interfaces. So again, we now need to think about, does router 2 need to participate in the routing domain or not? It doesn't necessarily have to. Normally it would, because we would at least want a management interface on router 2 in order to do like, SSH management, SNMP probing, logging, something like that. Because without IP routing, we're not able to send traffic into the routed domain or into the bridge domain. But without that, if we were to go to router 2 and simply say no IP routing, then it's essentially just doing basic bridging. So we define our bridge group. We'll say bridge 1 protocol IEEE. This is turning spanning tree on and essentially creating the CAM table, the MAC address table. Then on our two interfaces here, if we show run on router 2, we have interfaces gig00.23 and 24. These are the two that we are going to be bridging together. So on these links, gig0023, they're both in the same bridge group, and 24. Now this also means that we're now participating in spanning tree with the layer 2 switches. So from a physical design point of view, we would also need to look at how is the topology wired, and is this going to cause a problem when we bridge these two segments together? Because if router 2 here, for example, is the root bridge of the spanning tree domain, that might affect what's going on in the layer 2 forwarding. So normal VLAN type configurations that the switches support, the router does here as well, except this is under the bridge command. Like we could set the bridge priority. This would affect what's the spanning tree priority for the root bridge election. We could go to the link level and set things like the port cost, the port priority, same type of spanning tree options that we have from our regular catalyst switches. But with the minimum configuration, the only thing we really need to do is to say that the bridge group is configured globally and that these two interfaces are participating in that bridge group. If we look at the now show bridge 1, this is going to be the equivalent of the show MAC address table dynamic in the catalyst switches. This should show us what are the particular Ethernet MAC addresses of router 1 and router 3 on that segment. So if we were to go to router 3, and let's ping the broadcast address, if the bridging is working, we should be able to get a response back in from router 1, which we do. So as we know, broadcast traffic cannot be routed between interfaces. So based on the fact that we're getting our ICMP response in, it means that these two devices are in the same broadcast domain. Now they're not in the same VLAN, but they are in the same IP subnet, which goes kind of a little bit against normal bridging logic, but router 2 is connecting those two together. So if we look at the show bridge 1, we should now see that we have the MAC address that is associated with router 3. So it says if I have a layer 2 frame going to this MAC, it goes out this port, and then likewise going towards gig 0024, which is this one here. So between router 2 and router 1. So now on router 1, we should be able to ping router 3, which we can. So pretty simple configuration up to this point. It's basically just two commands on the router that's doing the bridging. So we're turning bridging on. We're saying that this particular bridge group is on the interface. Now also remember, in global configuration, I said no IP routing. If we were to leave IP routing on, which is the default, and then tried to bridge the traffic through the router, router 2 is now going to drop these packets, because the default behavior is that we either route the protocol or bridge the protocol, but not both of them at the same time. If we want to do both routing and bridging, we would either need to do CRB or do the IRB feature. So typically you would do this with IRB, but technically you could do it with concurrent routing and bridging as well. So on router 2, we would say bridge, run integrated routing and bridging. And for bridge group 1, we want to bridge IP, which is actually the default there, but we also want to route IP at the same time. If we now show run section bridge, we should see this syntax doesn't show up here. Bridge 1, bridge IP, this is the default. But we're saying for this particular bridge group, you're allowed to have a routed interface that corresponds to it, and you're also able to do bridging. So now router 1 and 3, again, they should be able to reach each other. Now again, it is important to test this basic connectivity before we get into our firewalling, because we don't want to be troubleshooting a problem in either the CBAC or the zone-based policy firewall when it has something to do with basic bridging or basic layer 2 reachability. So without any ACLs on the interfaces, without any of the zones configured, we should be able to bridge both broadcast, multicast, and unicast traffic between those interfaces that are in the same bridge group. Now on router 2 in the middle, if we were also to add this interface BVI, the number here corresponds to the bridge group number. So like on the switches, this would be the same thing as saying interface VLAN 1. So on the Catalyst switches, this SVI, the switch virtual interface, is the identical thing as the BVI on the router, except this is doing it in software as opposed to hardware. So on router 2 here, this is where we're going to put our IP address. We'll say 136.1.132.2. Now router 2 should be able to reach both of those devices, router 1 on the outside, and then router 3 on the inside. Now when we look at the firewalling implementation of this in the CBAC versus the zone-based policy firewall, this interface BVI on router 2 would now be considered part of the self zone for zone firewall. But in the case of CBAC, it's going to count as just a normal IP address on the interface. So we would, with CBAC, need to account for maybe OSPF traffic going to the router or telnet traffic, SSH traffic. We would need to account for that within an access list exception. But in the case of the zone-based firewall, we can use the self zone to determine what traffic is allowed to go to router 2, so outside to self, inside to self, or originate from router 2. So self to outside, self to inside. Okay, so let's look at our configuration up to this point. Pretty straightforward. We simply have first the bridge group configured. So bridge 1 protocol IEEE. Again, this is the same as like creating a VLAN on the switch. Then at the physical port level, we're applying the bridge group. This is like saying switch port access VLAN 1 on the switches. Then if we also want to have this layer 3 routed interface, we need to turn the bridge IRB feature on and then say we also want to route for this bridge group, bridge 1 route IP. Okay, without this, then we would need to turn routing off for IP. We would need to say no IP routing. Okay, next we have our firewalling configuration. So this is going to be a normal content-based access control config. There's not going to be any changes from the previous examples we saw. So we're essentially going to have two portions for this. We're going to have the inspection rule that is watching traffic leave the network. This is going to be our IP inspect. Then we're going to have an access list for our exceptions on the return path. So let's assume here that for our routing control plane, we're going to run EIGRP. So on router 3 and router 1, we're simply going to enable EIGRP on all the interfaces. So on router 1, let's just say router EIGRP1, no auto summary, and every interface is running EIGRP, so just network 0000. Same thing here on 3. Router EIGRP1, no auto summary, network 0000. We can see now we have the adjacency with router 1 because 2 is bridging this traffic between the two of them. If we show IP EIGRP neighbors and show IP route EIGRP, we can see that router 3 is learning, in this case, the loopback address of router 1. It says the next hop is router 1's IP address on this particular link. If we go and do a trace route to the destination, we should see that it's essentially one hop away. Now what this tells us is that the traffic is being bridged, not routed between the two of them. So router 2's BVI interface does not appear as a layer 3 hop in the path. The traffic is being directly bridged between the inside and the outside interface. Now since we are running IRB, router 2 can also participate in the routing domain where it could say router EIGRP1, no auto summary, network 0, and it should now form an adjacency both on the inside interface and the outside interface. But from a logical point of view, these are represented by the bridge virtual interface. So if we show IP EIGRP neighbors and show IP route EIGRP, it says the neighbors are located on the BVI and their routes are reachable through the BVI. When we look at the next hop values behind the scenes, router 2 is going to do an association between what is the layer 3 hop and what is the MAC address of that hop, basically by looking at the ARP cache. This is ultimately going to control what interface is the traffic bridged out. So we know that if we're sending traffic to 150.1.1.1 and it goes to the next hop 136.1.123.1, this address has this particular MAC address. If we show bridge 1 and we look for that address 94E8, it says this is reachable out gig 00.24. So ultimately router 2 in this case is making the decision based on the CAM table as opposed to the routing table, because the routing table doesn't show us the physical interfaces. It says that this needs to go to the bridge domain, and then the bridge domain should know it based on the MAC addresses. So if we were to send traffic to router 1 or to router 3, we could see essentially that the traffic is bridged between them. So it's one hop to those particular neighbors because we're in the same subnet and we're in the same bridge domain as both of them. If we look at router 1 or 3 and show IP route EIGRP, we should now see the routes to router 2 reachable via its BVI interface. So essentially this means that if we were to have other interfaces behind router 2, it would be able to send traffic into the bridged domain. So again, if we had something like gig 01 that goes to another router, router 4, and this is a regular routed interface, traffic is allowed to come in this direction and in that direction, assuming router 4 is participating like in the EIGRP domain. And again, this is what we consider then our integrated routing and bridging, that a portion of the network is routing IP, a portion of the network is bridging IP, and then we're integrating both of them together at the same time. Okay, so next let's move on to our firewall configuration. Again, as I mentioned, this is going to be two different steps. We have the inspection rule, and then we have the access list. So the inspection rule could match whatever traffic that we want to, just like our previous configs. So on router 2, we could say that we want to inspect, for simplicity, IP inspect, name is our CBAC rule. We want to inspect TCP, UDP, and ICMP. Now, of course, if we wanted the more specific application inspections, like HTTP, and then do more specific filtering on this, we could say, you know, what particular URLs are you allowed to get to or which are you disallowed from? This is going to be supported as well with the transparent firewall. But from a general point of view, TCP, UDP, ICMP, this is going to be probably 95+% of the applications that we're going to have going through the firewall. Okay, next we're going to apply the inspection rule to the physical interface, which from a logic point of view is kind of strange here that we're actually routing the traffic from the BVI, but the inspection rule is still going to be applied on our layer 2 interface. So this is kind of like in the catalyst switches where you're allowed to apply a layer 3 access list on a layer 2 switch port. So even if the port is not doing routing, if it's just doing bridging, you can also apply a layer 3 options onto it. And that's essentially what we're doing here. We're saying that as traffic is bridged to that outside interface, in this case it's going to be gig 00.24, we want to send the traffic through the inspection engine. So on interface gig 00.24, IP inspect, we have our CBAC rule that goes outbound. Now we also want to make sure that we have an inbound ACL for any of our exceptions that the CBAC engine cannot account for. So we'll have IP access list extended. We'll say outside in. And for right now, we're just going to deny IP any, and then generate some log messages. Then this access group, outside in, is applied inbound on the physical interface, not on the BVI. So if we look at the show access list, let's go to router 1 and ping router 3. Okay, previously we saw that router 1 was able to reach 3 because we had the bridging configured, we didn't have any security configured. Now on router 2, we can see that the ACL applied on the physical link is catching this as a deny, even though that we're trying to bridge the traffic between the interfaces. So again, it's kind of an odd configuration because you would assume if you're bridging, then the layer 3 option should be applied on the BVI, but this is an exception for that with the transparent firewall. Now, if we were to do the same thing from the inside out, if we went to 3 and did a ping to router 1, this is going to be allowed, and if we look on router 2 and look at the show IP inspect sessions, we can see the ping came from router 3's inside interface, it was ICMP, went to router 1, which means that the return flow should be automatically allowed. This means that other traffic from the inside, like a telnet to router 1, should be allowed, and we should see this in the session table. So we have our TCP port 23 for the telnet. But anything that is a non-standard protocol, same rules as before, like our trace route or like an IP phone call that we don't have the application inspection configured for, Router 2 is not going to know to allow this traffic back in the reverse through the state table. So on Router 3, if we were to do a trace route to Router 1, we'll see that this is denied by Router 2. And if we look at Router 2, we should see that the ACL says that we have the return ICMP codes, which is our port unreachable here, code 3, type 3, because we're trying to bridge it directly between 1 and 3, but 2 doesn't know how to allow this traffic back in the state table. So if we show IP inspect sessions, we should see those UDP flows that were the outbound trace route requests from 3 to Router 1. And again, the firewall doesn't know that the UDP outbound should be connected to the ICMP back inbound. So if we look at our access list outside in, we would still need to have our exceptions here. So IP access group, outside in, actually IP access list, extended outside in. We'll say permit ICMP any port unreachable, and then also time exceeded. Okay, we can see now the return traffic from Router 3, or to Router 3 I should say, is getting matched as a port unreachable. Okay, so now 3 should be able to trace to Router 1. Okay, let's also look at what happens when we clear the control plane. So if we go to Router 3 and say clear IP EIGRP neighbors, and let's do the same thing on Router 1, clear IP EIGRP neighbors. And we look at the log message that we have on Router 2, we can see that Router 2 is able to form the adjacencies with 1 and 3. But traffic from the outside, from Router 1 going to 3, this is getting denied by the inbound ACL. Now, we saw this problem before, which is basically based on the order of operations that we do our configuration. That we configured EIGRP and the control plane was working, or we configure OSPF and the control plane is working. We configure the firewall, everything looks fine, but then when there is a convergence event in the control plane, like a link flaps or we add a new router to the IGP domain, then there's going to be a problem in synchronization between the two of them. So we do need to take this into account whether we're dealing with either CBAC or the zone firewall, the control plane traffic to the router itself, or in this particular case, the control plane traffic that it is bridging between its interfaces. So we do not need to allow the EIGRP as it goes from the inside to the outside, but we do need to allow it as it comes from the outside back to the inside. And the reason why is that there's no application level inspection for protocol 88, which is EIGRP. Or same thing if we were running OSPF, protocol 89, there's not an application level inspection there for it. So again, this is the reason why that on the firewall, at least for the lab purposes, you would want to make sure to end the access list in an explicit deny with log. So any packets are dropped, we can see from the messages here. So we now know that for access list outside in, we need another exception that says to permit EIGRP. Now, of course, we could be more specific. We could say the individual EIGRP unicasts from 1 to 3. But we could see now we have an adjacency from 3 to 1. This message here, it says that the retransmission limit exceeded. This is usually an indication that there's some sort of one-way communication in EIGRP. So router 3 is getting the multicast hellos in from 1. Then it's trying to do unicast synchronization of the EIGRP topology, and it's not getting an acknowledgement back in. So it's basically sending the updates out and not getting the acknowledgements. This is what it means that the retransmission limit is exceeded. So if we test the reachability both ways, we would have seen from that ACL that router 2 was dropping the EIGRP return traffic outside to inside. So beyond this, though, the configuration of router 2 is basically the same. So if we look at the full final config, we had the bridging, which was to configure the bridge group, apply the bridge group at the link level. Then if we're also doing routing of IP, we need to say for this bridge group, we're routing IP, run the IRB feature, then we have our firewall config. So under the inspection, we're saying these are our rules. So inspect TCP, UDP, ICMP. Then this is applied directly to the interface. So again, even though we're not doing our routing here, the layer 3 configuration still goes on what is essentially now just the layer 2 interface. Okay, any questions up to this point on the CBAC configuration for the transparent firewall? Okay, there's a question, do we need to configure both the ACL and the inspection rule? So let's take a look at that on router 2. What were to happen if we simply removed the ACL that we have configured on the interface? So this interface, gig00.24, this is our outside interface. So we have that configured, the ACL is outside in. So let's say on gig00.24, no IP access group outside in inbound. If we now go to router 1, which is on the outside of the firewall, and try to ping to the inside, the traffic is allowed. Here, same thing like a telnet. So again, in the case of the content-based access control, the IP inspect, you do need the ACL in order to enforce the deny. The other option for that is if you were to use the block TCP non-session, that would deny the TCP traffic that is not part of the state machine, but it would not deny the other IP protocols like UDP, ICMP, IPsec. Those would not be subject to drops. Now in the case of the zone firewall, we saw that was different because the zone firewall inspection ends in class default, and class default's default action is to drop traffic. So with zone firewall, you don't necessarily need the ACL, but in the case of CBAC, you normally would want this to drop the additional traffic flows. Okay, there's another question here. Can we create an inbound permit for EIGRP to form the neighbor relationship? That's essentially what I was doing with the access list here. So on router 2, if we look at the show access list, this line number 3, permit EIGRP any, this is allowing traffic to come originated from router 1, who is on the outside, and then send an unsolicited EIGRP message to router 3. Because EIGRP is not a client-server protocol like BGP is. It's going to be coming from the inside to outside, and it's also going to be coming from the outside back to the inside. And since router 2 does not have an inspection for protocol number 88, that's why we need to do this exception, to say that the particular control plane protocols need to be allowed as an exception to the firewall. Now there's an additional control plane exception here that you'll see in the documentation for this feature that is to allow DHCP pass-through on the router. And the reason that you would need to do this would be that if, and let's go back to our diagram here, if we were to say that router 3 was the DHCP client and router 1 is the DHCP server, router 2 cannot inspect this traffic because it is coming from 0000 going to the all broadcast address. So this is our UDP. Basically, this is the DHCP discover message. So in the case that you're doing transparent firewall and this interface is running DHCP client, you would need to say IP inspect L2 transparent DHCP pass-through. So it says when the source is all zeros and the destination is all 255s and it's UDP, and it's these specific ports, which is the bootp client going to bootp server, then the traffic is allowed through. So it says DHCP has been seen, pass-through flag allows the packet. And you can see this in this particular case. If we were to go to router 1, and let's say we configure a basic DHCP pool. So IP DHCP pool VLAN 24, where the network is 136.1.1230/24. Then on router 3, on the interface here, we say IP address DHCP. Now, right now on router 2, we do not have the access list applied on the interface. If we look at the show IP interface brief, or not on router 1, on router 3. Router 3, if we show IP interface brief, we're asking for a DHCP request, but it's getting denied. If we were to go to router 2 and say, now globally, IP inspect L2 transparent DHCP pass-through, and look at router 3, we should see that it gets an allocation. So let's shut down the interface and then bring it back here. There was another question here. Could we create a router to do a relay? Yes, that would also work, because if we were to take the broadcast traffic and then change it to a unicast, the firewall can inspect a unicast UDP traffic. It's a problem with the broadcast traffic that it can't inspect. The same would be true if, like, you did maybe like a network address translation and changed it to something that it didn't inspect, or like you did a GRE tunnel over it. The issue is that it's these broadcast DHCP discover messages that it doesn't know what to do with. And let's debug a DHCP, actually debug IP DHCP server would go on router 1. Debug IP DHCP server packets. And on the client, this would be debug DHCP detail. So it says we're sending the discovery. We're sending it out that particular interface, F00.23. So router 3 sends the discovery out. Let's see, did 1 get it? Which it looks like it didn't. Probably what happened here is that this inspection, this probably doesn't take effect until we reset the engine. So let's do this here. Let's shut the interfaces down on router 2. So gig 0023 and 24. then bring them back up. And that particular debug they were showing was debug L2 firewall and L2 firewall DHCP. So let's see, what is the specific command here? It should be debug IP inspect L2 transparent. So let's say packets and let's say DHCP pass-through. Says here the source is 000 going to broadcast. Came in on gig 00.23. DHCP packet is seeing pass-through flag is allowing the packet. Input interface gig 0023, output is gig 0024. So we should be able to get the packet to the other side now. And on router 1, let's say show IP DHCP. Show IP DHCP bindings. It should be able to receive this packet in. Now, sometimes when you test some of these features out and you're doing broadcasting, there can also be a problem with the catalyst switch that's in the layer 2 transit path. Because if we look at here basically our physical topology versus the logical topology, router 1 and router 2 are physically connected to the same switch. So there's certain cases that if router 1 sends the broadcast out, it gets bridged to another portion of the network and then comes back in, that the switch is going to discard the packet because it basically sees it as a bridging loop, the packet going in and out the same interface. So if we change this design and moved router 2's interface over to gig 01, it's probably not going to be a problem if it's going in and out 2 different physical paths. Now, within the scope of the lab exam, if they were to do a question like this, doing the transparent firewall or doing bridging, they would take that into account and make sure that the topology is set up purposely to allow that. But the switches can essentially find a loop in the data plane and then throw the packets away if they see it looping between the interfaces that are between 2 interfaces that are in the same bridge domain. But we can see basically the point of this is we don't need to see the full functional DHCP, but we see when the firewall intercepts it, it says it was DHCP, so we're going to pass it through. And then the way that we're doing this is to flood it from this interface, gig 023, out to interface gig 024. Now we'll see that when we look at the transparent firewall in ASA, it works a little bit differently here than it does in a regular iOS, and not all of these control plane flows are going to be allowed by default. So we'll see that the traffic coming in on the inside of the ASA is treated differently than in on the inside in iOS. And it depends on whether we're doing unicast bridging or whether we're doing broadcast and multicast. But we'll come back to that when we talk about the ASA running the transparent firewall.